Non-holonomic agents are commonly used to represent real and virtual entities ranging from vehicles to people. Many applications would benefit from optimal paths for non-holonomic agents, including video games, robotics, and crowd simulation. To this end, we extend the literature on optimal non-holonomic paths by looking at agents that accelerate from a standstill. As contributions, we derive the arrival times of accelerating agents to their destinations, derive a numerical surface for choosing the optimal path, and then show how to choose optimal paths in real time with little or no error. Key to our approach is the acceleration angle threshold, or the moment when an agent begins accelerating linearly. In this video, the green agent has a threshold of pi, the blue agent has a threshold of pi halves, and the red agent has a threshold of 0. Note that an agent can have any threshold between 0 and pi. In this example, the agent with a threshold of pi halves arrives soonest of the three, but there exist destinations for which any threshold is optimal. To find the optimal acceleration angle threshold for an agent, and hence its optimal path, we begin by looking at agents with a threshold of pi. The height of the surface gives the arrival time of an agent with a threshold of pi using our equations. The higher the surface, the longer it takes the agent to arrive at a destination. Contour lines are placed at every second. Notice that this surface is almost radially symmetric, and that there are no jumps as we move from pre-full velocity destinations to post-full velocity destinations. Details in the paper. Using our equations, we can find the arrival time and path for an agent with any acceleration angle threshold. Once this is done, we can numerically derive the surface for choosing the optimal path for an agent. This surface shows the optimal acceleration angle threshold based on an agent's destination. The higher the surface, the higher the optimal acceleration angle threshold. Deriving this surface would take too long to run in real time. Thus, we propose a low-error method for approximating the surface. Notice that the surface has a clearly flat region. We call this the Plateau Region. Using this Plateau Region, we can break the surface into two parts and find an agent's optimal path in real time. We validate our work using quantitative error analysis. In every case, our error was minute, giving us great confidence in our results. Thank you for your attention.